SwayamPrabha. Digital India. Educated India.
Welcome back to this series of lectures on elements of solar energy conversion. Now we are here at lecture number 8. Okay. So, like any other lecture, we will quickly tell you what is covered so far. So, in first 7 lectures we have covered the basic concepts on sun, earth and their relationship. Okay. Then we have covered the calculation of time. Third major thing we covered is the solar spectrum. And then we covered the role of atmosphere. Next we started, or we also covered this prediction of radiation availability. And we have started in the last class the important angles and their correlation. Okay. This is where we are at this moment, and we will take it forward in this lecture. So, in the last class we stopped in this particular figure. Okay. So, what did we see? We have a horizontal plane at this point P, and then the reference frame origin for this case is the center of the earth, and then we have taken this x and y axis in such a way that x y makes the equatorial plane, and x is the x axis is the projection of the sun ray that is coming directly to the center of the earth. Okay. Now we have looked at few angles in these combined reference frame. Okay. So, first one was the angle between the projection of sun rays to the horizontal plane and the projection of the location of the observer. Okay. So, basically OX is the projection of sun rays on the equatorial plane, and OQ is the projection of OP vector on the equatorial plane. So, angle between them is the hour angle. Okay. And we have also looked at the angle that the observer center of the earth connector OP, that is making with the equatorial plane, that is the latitude L. Okay. What other things did we look at? Another very important angle we have looked at is the angle between the sun ray and its projection on the equatorial plane. This is the declination angle that we have looked at, delta. Okay. and the fourth angle that we have looked at is the angle between the sun ray and the vertical line or the normal to the horizontal plane. That angle is our zenith angle theta z. Okay. Now, another thing we can look at is the angle between the sun ray and its projection on the horizontal plane that makes with the south direction. Okay. So, if we have so what we can say that let us take the projection of the IN on the plane to be this one. Okay. If this is the projection, so this is projection of the sun ray on the horizontal plane. Okay. So, that particular projection whatever angle it makes with the south direction, what is that? You know that, right? So, please think and find out that angle before you proceed. So, let me now tell you the angle to be the solar azimuth angle AZ. Okay, this angle is AZ. And another angle of interest here is the angle between the sun ray and its own projection. What is that angle? That angle is alpha or solar altitude angle. Okay. So, now we have identified all these angles and now we are in a position to interrelate them. Okay. So, let us go to the next screen and see that just by inspection or from the definitions, actually from the definitions, what we can see is the solar zenith angle and the solar altitude angle, these two are complementary to each other. Okay. So, alpha plus theta z, they will make you a right angle. Okay. This is the altitude angle and this is the zenith angle. So, here I want to stress that all these symbols that we are going to use like alpha, theta z, az, L, phi, all those things, they signify a particular angle, right. So, for all the derivation we will not see or we will not say that this is the altitude angle or that is the zenith angle and all these things. Okay. So, what will we do? We will assume that you recognize that alpha means altitude angle, theta z means zenith angle, and for that to be true, that assumption to be true, you have to do these go through these notes and go through these lectures many times, do examples on this, and then only you will internalize all these naming system as well as you will grow intuition in terms of visualizing this 3-dimensional thing and interconnection between two reference frames, and that is very, very important. Okay. So, that is the first relation we get, alpha plus theta z equal to pi by 2. Now, say the vector OP, okay, this is the vector joining the center of the earth and the location of the observer. Okay. So, if you look at this vector and if you write the corresponding direction cosines, okay, for this vector OP, then what we can write? Let us say the direction cosines are A1, B1 and C1, okay, with respect to the x, y, z coordinate that we have shown earlier, coordinate system. Okay. And similarly, we say that the vector I n, which represents the direction of the sun ray, okay, which is actually direction of the sun rays. Okay. So, let us say corresponding to that vector, the direction cosines are A2, B2 and C2. Okay. So, if that is the case, now we have to find out what are the values of A1, B1, C1, A2, B2, C2. Okay. So, for OP vector, what we can write, this A1, which is the direction cosine in terms of the x axis, what we need to do? We need to first bring it to the equatorial plane, xy plane, that is, for that we have to multiply it by cos L, the latitude of the observer. Okay. And then within that xy plane, if we want to project it on the x axis, then what we need to do? We need to multiply it with cos of omega, that is the hour angle. So, this is, so for few times initially I will repeat what angle is what, okay, and this is hour angle. Okay. So, please go back to that figure and ensure that you understand each of these direction cosines, how we are getting it. So, A1 is cos latitude multiplied by the cos of hour angle. What is the other direction cosine? That means towards the y axis, what would be the direction cosine? There we will find, again we have to bring it to the equatorial plane or xy plane by multiplying it with cos latitude, and then to get the y component, now we have to multiply it with sin omega. Okay. Instead of cos omega, now we have sin omega. Now, the third, the z axis direction cosine. Okay. For that we only have one angle dependence, sin L. So, if we go back and look at this figure, we can see that for the vector OP, if you want to come to the or if you want to project that to the equatorial plane xy, you get this OQ, right. Now, OQ, from this you can, to get OQ you have to multiply it with cos L. Okay. By cos L you get OQ, and then if you want to project to the x axis, then you have to multiply it with cos omega, and for the y axis you have to multiply with sin omega. Okay. And all these things are happening in the xy plane. Now, if you look at the plane that is making this z, if we say this point z and then P Q O, in this particular plane Z P Q O plane, the z axis projection would be sin L, okay, or the sine of latitude angle. That is how we are getting the direction cosines. And here I should mention that we have taken a left handed coordinate system, and that is why we get all of these direction cosines in positive value. Okay. So, positive direction cosines. Okay. If you take right handed, one of them will be negative. Okay. Fine. Now, the other important vector is the vector I n, which represents the direction of the sun rays. Okay. So, now if we consider the corresponding direction cosines, sorry, this will be A 2. Okay. This particular direction cosine will be in the with respect to the declination angle delta, right. So, we will have it cos delta, because that is how the x axis is chosen. We have chosen the line which is projection of I n on the equatorial plane to be our x axis. So, this is straightforward cos delta. Okay. And the second direction cosine B 2 will be 0, because that is how the x, y, z coordinate system is chosen. If you are cutting one axis completely in one plane, the same plane, the other axis will be 0, and C 2 will now be sin delta. So, this is much simpler in terms of it just depends on single angle. Okay. So, depend on the declination angle only. That makes sense, right. So, declination angle tells you with respect to the axis of the rotation of earth where the sun is, okay, at any given point of time. So, that makes sense that the direction cosines with respect to the reference frame, which is centered at the center of the earth, will only depend on the declination angle, and here the dependence is on latitude and hour angle. Here also it makes sense, right. So, here we are looking at the observer location with respect to the center of the earth. So, it does not depend on anything that is related to the sun, but it does depend on how much with respect to the prime meridian it moved in rotation direction. So, that is the hour angle, and where it lies in terms of the latitude. Okay. So, that observer position, that matters. Okay. Now, once we have these two direction cosine sets for these two vectors, now we are in a position to find the angle between these two vectors. One is OP and the other one is IN. Okay. So, how to find that? By taking a dot product. Okay. So, you know the dot product will give you the angle between them in terms of cos. And let me go back to this figure where the angle between IN and OP we can see. Okay. Let me take this color. So, you can see here that OP, when it is getting extended, we are getting this PV vector, right. When OP is getting extended, we are getting this PV vector. So, the direction of OP and PV are the same. Okay. So, whatever angle that P v vector is making with respect to I n, that is our angle between these two, and what angle is that? That is theta z, right, that is the zenith angle. So, now if we see that, then we can directly write this cos theta z, which we will obtain in terms of in the form of dot product, and that is by definition direction cosines multiplied and added, right. So, A1 A2 plus B1 B2 plus C1 C2. Okay, that is how we get the cosine of theta z. Now, you take the values from values that we have obtained, and you directly can write this. This will be cos L cos omega cos delta plus sin L sin delta. Okay. So, this term actually giving rise to the first term, okay, and the third term is giving rise to the second term, okay, and this particular thing is contributing to 0 because your B2 is actually 0. Okay. So, that is how we get, and this is a very important relationship. So, let me write it again to put emphasis on it. So, this is an important relationship. This we will use again and again in many occasions, and actually we have used it already. Okay. You please look back, we have used similar equation already. Okay. So, now we have derived that equation as well. So, now if we look at this theta z, we already know that theta z plus alpha is equal to pi by 2. This we have seen, right. So, you can write, and what does that mean? That cos theta z equal to sin alpha, right. And if that is the case, then you can write sin alpha equal to cos L cos omega cos delta plus sin L sin delta. Okay. So, both the altitude angle and zenith angle you can obtain by this formula. So, this is very straightforward, but very important relationship. Okay. And another thing I should note here, that whatever we are talking so far in this particular figure, we are talking of a horizontal plane, right, and that is why the normal is actually towards the vertical direction. The normal is making an angle of zenith, that is theta z with the sun rays. Okay. So, often for these horizontal planes, theta I, which is, we have seen that it means incidence angle, is designated as theta h. Okay. H stands for horizontal plane. Now, so for horizontal plane, this theta z is equal to theta h. Okay. So, sometimes it is given that your zenith angle is this, and or something is given, you have to find out the zenith angle, but it is very important to know that zenith angle is the same thing as the angle of incidence for a horizontal plane. Okay? That is why I am putting this note here. Okay? Now, we will look at several other important relations. First is, if we now apply a tilt angle. Okay. So, if the plane is not horizontal, but tilted, okay, and if it is tilted by an angle beta. Okay. This beta stands for tilt angle all the time. So, again you have to remember that whenever you see beta, it means tilt angle. Tilt angle means the angle the plane makes with the horizontal plane. Okay. Or you can also say in terms of the surface normal. So, the angle the surface normal of the tilted plane makes with the vertical direction, that is the angle beta. Okay. Now, very interesting thing we can observe now. Let me just draw a figure of a cut in the earth. Okay. So, let us say this is the center of the earth O, okay, and let us say that we have at certain location C, we have a plane which is, so this is the horizontal plane, which that means the plane that is perpendicular to this OC line, right. So, OC and let us say V, this particular vector is the vertical direction. It connects to the center of the earth and position of observer, right. Now, whatever plane is perpendicular to that direction, that is our horizontal plane, right. So, this is horizontal plane, right. So, suppose we have a collector which is a tilted surface and it makes angle beta with the horizontal plane. So, let us say that we have a plane which is making an angle beta here with the horizontal plane. Okay. So, now we have to find all the relationship with this tilted surface, right. So, it is little difficult, but we can make it super easy. How? Let us say that we draw a parallel to this wherever it takes. In some other location, you draw a parallel line to this tilted plane. Okay. So, this is what parallel plane to the collector which is a tilted plane, located at the position C. Okay. So, somewhere on the earth you will actually doing this, and what is that position? Let us name them and name that point to be D. Okay. So, similar to what we did at C, what we can draw at D, we can draw a line that extends along OD. Okay. Now, you can imagine that this particular parallel line, wherever it is cutting, this is the horizontal plane at location D, right. So, the same plane, so the same plane is also a horizontal plane at location D. Do you agree? Right. So, if that is the case, then what can we say? We can say that a surface located, so this is what we observe. Okay. So, a surface located at the latitude L. Okay. So, let us say the latitude here of the original position C is L, and the latitude here for the point where the horizontal is parallel to the collector, that is L minus beta, right. Because you can see that if this particular plane, this particular collector plane is parallel to the horizontal here at D, then the latitude has to be L minus beta. They are on the same plane. Okay. This whole thing is not a 3-dimensional thing, but you can think of all the things are lying on the plane of this board. Okay. So, this angle is L minus beta, this is very important. Now, so a surface located at the latitude L tilted towards the equator, this is an important clause, we will see what it means later. So, tilted towards the equator at an angle, or I should say at a tilt angle beta is simply parallel to the horizontal plane at the latitude L minus beta. True. So, that is a very significant observation which will make our life much easier when we talk about the tilted plane. So, for tilted plane, what we can write, that the angle of incidence is obtained using the same formula as used for a horizontal plane. Okay. But the catch is by replacing L by L minus beta. Okay. How easy is that, right? So, we have seen earlier that theta z is the angle of incidence on a horizontal plane, okay. And we have also seen that this cos theta z is your cos L, cos omega, cos delta plus sin L, sin delta, right. Now, you want to find this angle of incidence, let us say that is theta t, t stands for tilted. So, this is angle of incidence for tilted surface. So, what we can write? The same thing cos theta t now we can write, and we will replace this L by L minus beta. Okay. Everything else stays the same, and here also we have one L. So, we have to replace that as well. Okay. This is super easy, right? Just by a simple observation, you did not have to go through all the different manipulations, you just change the latitude by L minus beta. Okay. So, as if it is a correction factor. Okay. So far so good. Now, from these relationship we are in a position to make some important observations already. Okay. So, first of all we have talked lot about solar noon, right, while we talked about the solar time, clock time and all those things, we talked about solar noon. So, what is that? Solar noon is what we call when the sun is at the topmost possible position for that particular day. And how it is defined? It is defined when the hour angle is 0, right. So, that is how it is defined. Okay. Now, in this particular equation, if we put hour angle to be 0, so we have this, sorry, we have this okay. So, if this omega hour angle is 0, then what we can write? This cos theta z is nothing but cos L cos delta plus sin L sin delta, because cos omega is 1 now. Okay. So, is the right hand side familiar? It is, right. What is that? It is cos of L minus delta, right, cos A cos B plus sin A sin B. So, cos A minus B. So, both sides are cos. So, what you can write? Theta z to be L minus delta. Neat, right. So, at solar noon this particular zenith angle will be equal to L minus delta, and you can note here that here, so it tells you zenith angle is what? The it corresponds to the maximum possible altitude angle, right. That means how much you have to look up to look at the sun directly, starting from the horizontal plane, how much you have to look up. Okay. So, here we can see that this zenith angle depends only on the latitude, with what it signifies the position of the observer, and the declination angle, that is the day of the year. So, for a particular location, suppose you are at Hyderabad, for that particular location, for a particular day of the year, you know exactly how much the sun will go up in the sky. So, it depends only on the location and the time of the year or day of the year. Okay. Now, the other thing that we can note here is that what is the sunrise or sunset angle. Okay. These we have used, right, when we talked about the prediction of solar radiation availability. Do you remember? We have used this SA prime, SA bar and SP bar, all these quantities, they all depended on this WS and W, right. So, the sunrise and sunset angle, first of all, what do they mean? They mean the lowest position of the sun in the sky. Of the sun in the sky, right. Lowest position means what? The horizontal position, horizon, not horizontal, but at the horizon, that is the lowest possible position, right. So, sunrise means at the horizon it is moving up, and sunset means at the horizon the sun is going down. Okay. So, both sunrise and sunset correspond to alpha equal to 0, right. When you are at horizon or the sun is at horizon, then the altitude angle is 0, right. You do not have to look up at all. So, both of them, that is in two different directions, but both correspond to alpha equal to 0, and both are placed symmetrically around the solar noon. Okay. So, if we want to find out this sunrise or sunset angle, what we need to find? Why we need to find how much is this when alpha equal to 0, right. That is the question we are asking. Okay. Now, how to find this? Again, let us take the equation. So, we know in terms of the altitude angle, we have this equation sin L equal to cos L, sin alpha equal to cos L cos delta cos omega plus sin L sin delta, right. This we have seen earlier. So, now for alpha equal to 0, sin alpha equal to 0. Okay. So, we have cos L cos delta, and now we will write this omega to be omega s, because it represents either sunrise or sunset, right, plus this does not change. Okay. Now, if you bring this in one direction, I mean this, if you find out, simplify this equation to find out cos omega s, what you get is minus tan L tan delta, right. So, what you can write is cos inverse minus tan L tan delta, and for a particular location L and a particular day of the year delta, you will have two values of the one value of this omega s, and positive one, positive omega s will mean sunset and negative omega s will mean sunrise, right. And now we know exactly how to find this. This formula also we used earlier for predicting the solar radiation availability. Okay. And we also know, we would like to know the day length, right. Day length will be what? It will be just the difference in time between the sunrise and sunset. So, it will be just 2 into omega s. Okay. Now, this is in terms of angle. So, if we want to know day length in hour, then we will have 2 omega s divided by 15, because 15 degree is equivalent to an hour. Okay. So, that is how we get the day length. Again we have used this day length in solar radiation prediction, and we have derived them now from first principles. When we combine these two reference frame, one is centered at the observer, the other one is centered at the center of the earth, we obtain the interrelationship and we derive these equations. Okay. Now, one thing, so both these sunrise, sunset, okay, and solar noon we have talked about with respect to the horizontal plane, right. We have assumed that we are on a flat ground or field and it is horizontal, and we want to see the sunrise sunset from there. But for a collector, the sunrise, that means when the sun radiates on it, starts radiating on it, that is sunrise, and when it stops radiating at it, which is sunset, can be different compared to the horizontal plane, can be different if there is a tilt. Okay. So, with respect to the collector plane, the sunrise and sunset we have to re-evaluate, or we have to make the correction for the tilt. Okay. So, what we can write? We can write the same thing, and similar way we will correct it by correcting the latitude. Okay. So, this is a very simple relationship we just obtained from a simple observation by correcting the latitude. So, this is omega s prime is the sunrise hour angle with respect to the tilted plane, okay, and this is the latitude correction by the tilt angle, and the same formula tan latitude into tan declination. This formula has been used to obtain the sunrise hour angle for a tilted plane as well. Okay. So, now few notes I should mention, that the hour angle determines the position of the sun with respect to the solar noon, right. So, that is fine, but solar noon is a very local thing, right, is a local thing. because we have seen that as the solar noon are different at all the different points, that is why we had to take one standard latitude against which all the clocks will be calibrated. Okay. So, that local thing we cannot make something very generalized. Okay. So, to get a generalized relation, we need some global reference frame. Okay. So, this omega or hour angle has to be in terms of the global reference frame. Okay. So, the hour angle has to be related to the global frame. And what is that global frame? Is the north or south direction or east or west direction. These are global thing. Even if you are here, when you tell you are looking at south, you are looking at the south pole of the earth, right. So, that is the direction of south. So, that is the global reference frame. So, it needs to be correlated with global north, south, east, west directions. Okay. In that case, it will be a general relationship, you can use it for any location. So, that is a very important requirement that we have. Another thing we need to mention here is that so far the tilt is given towards the equator only. So, if we look back where we mentioned it first, yeah. So, here you note that I mentioned the tilt is given towards the equator. Okay. So, this particular assumption is there, but it may not be always true, may not be always true. So, we need to again generalize it. We need to consider the surface azimuth angle. Right. The surface azimuth angle is represented through AZS. Okay. Again I remind here that AZ is your solar azimuth angle. So, please do not get confused between these two. AZ means solar azimuth angle and AZS means surface azimuth angle. Okay. And both of them contain S, solar also contain S and surface also contains S. So, that is why it is important to remember what we mean exactly by AZ or AZS. Okay. So, our requirement is to generalize the analysis and express omega in terms of global south. Actually, if you fix it with global south, then the whole reference frame is fixed. you just do not need to fix it with global north, east, west, all those things, just one direction is fine, and we have chosen that to be south. The other one is the tilt of the collector plane can have an orientation other than south direction, and hence it can have a value of surface azimuth angle. So, with these two goals, one is this, other one is this. With these two goals, we will now delve into a problem where we will do a completely generalized analysis, and this is little more complicated than what we saw in today's class. And here I stop, and we will start this new analysis in the next class.